Hey, hello class. So this is video 3 in section 4.9. In the previous video, we talked about how you can find all antiderivatives of a function by simply finding a unique one and then adding c as an arbitrary constant. That's what we did in the previous video. Now, I don't want to be writing all of the time. I don't want to be writing all antiderivatives of cosine 4x have the form hx plus c, where c is an arbitrary constant. I mean, I can do it, but it's a lot of work. So it makes sense, instead of doing that, defining notation for all antiderivatives of a function. Right? So how do we do that? So given a function, f, we will denote, so this is what I was writing every time, all antiderivatives of f of x on some interval I by, well, instead of writing all that, now we're just going to write this. Like that. Now, of course, that looks weird right now. Okay, what are all these symbols, right? I recognize the f of x. I should recognize d of x, right? Remember dx we saw before. Sorry, not d of x, just dx. We saw before when we were doing linear approximations, right? And dx just meant the change in the x variable or the horizontal axis. And then we have this symbol here. Now, for now, don't worry about what these things mean or where they come from. Just notice that this here is going to stand for all antiderivatives of f on an interval I. Now, a few things I can tell you. This part here, this is called the integrand. This part here is called the variable of integration. And this here is the integration symbol. Let's call it like that. Kind of looks like an S, like a stretched out S. Okay. Now, again, this will become clear why we use this notation once we get to chapter 5. For now, just use it, right? So if I ask you to find all antiderivatives of a function, you're going to use this notation. Okay. So, for example, before, in the previous video, we saw that all antiderivatives of cosine 4x have the form 1/4 sine 4x plus c, where c is a constant. Now, instead of writing all this, we're going to write the same thing like this. This is going to be the same thing as the integral, and this is how you want to read this, the integral of cosine 4x dx equals 1/4 sine 4x plus c. And again, this here means all antiderivatives of cosine 4x on some interval. So instead of writing all that, we can just say, okay, we're trying to find all antiderivatives of cosine 4x, just put it inside this notation. So change the integrand with cosine 4x. And that's it. So you see that we simplified the notation. Now, one last thing to say. This here is called an indefinite integral. Now, of course, this still doesn't make much sense. Why is it called an integral? Why is it indefinite? You'll see that there's another form of integral that's called definite, and they're different, right? But for now, whenever you see this, you want to think of it as two things. So whenever you see the symbol integral of f of x dx, you're going to think two things. What are those two things you want to think about? Well, think this is all antiderivatives of f on some interval. And also, this is the indefinite integral of f of x. And it's safe to write the, and in fact here I should have just written the in the previous slide, right? Because as we know, we can find all of them, right? So this is the indefinite integral of f of x. So whenever you see that notation, integral of f of x dx, think all antiderivatives of f on some interval, and also think the indefinite integral of f of x on whatever interval we're working at.